Hello YouTube! Today we're going to talk about mechanical work. So in particular, we're going to be sort of getting into how you change an object's energy and the ways that you figure that out. And we're going to start at it a little bit weird, but we'll get back in eventually. Ideally, end of the day, you should be able to find the work that is being done on an object by a variable force. That's the hard one involving calculus. It's also going to involve some vector math, in that we'll need to learn what a dot product is, and then we'll also need to generate and evaluate the equation for work in terms of the force applied over a distance. If the dot product stuff is fuzzy, or if you felt like it went too quick, we can do like a full video on the dot product. It's not too bad, but just in case, let me know. So what is mechanical work? Well, definition of work is it's the amount of energy given to or taken from an object by a force. So unfortunately, the definition of work is based around energy, and there are definitions of energy based around work. So mostly it's just this math thing. You take the force, you multiply by the dot product of the distance traveled. If it's a constant force, you throw your pen halfway across the room, and that's work. Conceptually, the way that I like to approximate it is that energy is the amount of stuff you could do, whereas work is the stuff that you actually do, which requires energy in order to do it. As we're talking about work, it's important to recognize that a force can only do work on an object if the object moves, and if the force has a component that is parallel to the direction of motion for the object. There's a pretty basic reason for this, which is that if you are moving sideways, getting pulled up isn't contributing to that. So if the object is moving sideways, the thing that's actually causing a change in its motion will only be forces that are parallel to that. So the thing that's causing a change in its energy will only be forces that are parallel to that. Quick word of warning, that's sort of a pitfall that you can fall into. When you're calculating work done by forces, really only worry about non-conservative forces. Don't do this for springs. Don't do this for gravity. You really don't have to when we get to the work energy stuff that's combining the two, specifically because you've already done that when you include the existence of potential energy. Cool. So the simpler version of this equation is that work is equal to force dot product with distance, because both of those things are vectors. And what that is the same thing as saying is the component of force that goes the same way as the distance, or the component of the distance that goes the same way as the force. Those two things will be equivalent to each other. A way to find this is to take the force and multiply it by the distance times the cosine of the angle between the two. So in particular, if you've got a force, and you've got a distance that the object travels while that force is pushing it, there should be an angle between those two things. And if you want to find the component of force, let's pick a color that's not going to be bad for red-green colorblind people. If you want to find this component right here, this will be f times the cosine of theta. And so f cosine theta will get you this component, which is the parallel component to the direction of travel. Multiply that by the distance, and you'll get your work. The units for work are joules, same as energy, for reasons that'll become very apparent later, but basically because work is the amount of energy you have spent, it's energy. F is your force that's measured in newtons. The dot between the two is the dot product. It's one of the two types of vector multiplier, and it returns a scalar. So work is actually a scalar and not a vector. It doesn't have a direction, but it can be positive, meaning gaining, or negative, meaning losing. Which isn't normal, because normally we've been doing positive as forward and negative as backwards for vector math, and this is one of the ones that's not. D is the distance traveled by the object. and along that line while that force is being applied, and theta is the angle between the vectors of force and distance, which will be measured in degrees or radians. Because it's going in a cosine function, it won't matter which. If the theta is ever outside of a cosine function or sine function, it's probably going to have to be in radians, which will become relevant in later units, though not this one. Cool. All right, so we're just going to do a couple example problems on some sort of easier situations. And then we'll do an example problem that involves some calculus for how to do this when you have variable forces. So that equation only works with either, and I should have probably stressed this, average force. So let's actually go back and put that up. Average or constant only. If you have a variable force, this will not work and you'll have to do calculus, because of course you will. All right, so our two problems are, we've got a person who drags a box 40 degrees along the ground using 30 newtons of force for 5 meters from rest. And then our second problem is, what is the work that is required to lift a 10 kilogram box along the path shown? At a constant velocity is something that's actually pretty relevant to that last one. So, doing that out, we've got our first one is a box, and that box is being dragged at a 40-degree angle to the ground using 30 newtons of force for a distance of 5 meters from rest. So for A, if we want to find our work, there's no A, there's just number 1. Our work is going to be equal to F d cosine of theta. We have our force, it's 30. We have our distance, it's 5. We have our cosine of 40 degrees. So our answer will be 150 times the cosine of 40 degrees. It will be positive work, because these two match. If you put in the cosine of, and I should have had an example with this, if it was pulling it backwards, you would not want to use the 40, although you could if you explicitly knew that it would wind up being negative. You actually need to use the 140 degrees instead, specifically because it's the angle from this one to this one, or from this one to this one. Those are the same as each other, and that'll be what gets you the correct sign on the work. The sign's not going to matter too much if you want to just be like, okay, well, whatever, I know it's pulling it backwards, so it's taking energy away from it, so it winds up being negative. That's fine too. So a couple quick takeaways. If they go the same way, it's positive. Opposites mean negative for this, because it's either helping it move faster or it's taking away kinetic energy or some other type of energy by stopping it from moving in that direction, or trying to anyway. All right, so that's it for number 1. Super straightforward. For number 2, there's a little bit of a trick to it, which is specifically that if you are pulling this thing at a constant velocity, you are going to need to pull it such that you've got some force on it. And that force is going to be at some angle. And when you do that, it's going to need to go in some direction. This one is easier to think of as the requisite force required to lift it up, and the component of that force, instead of worrying about the component of that force that's parallel to the way it's moving, worry about the way it's moving that's parallel to the force you have to use to lift. And if you want to lift this sucker up at a constant velocity, you're going to need an upward force that'll counteract the force of gravity. So this force is going to have to be mg. And if you want to lift it up for that distance, the height will be the parallel component of the distance that you travel. So what we can do is we can just say that our work is equal to our force times our parallel component of distance, because we have a variable angle. So it's harder to do it with cosine theta. But it's easy to say, well, the force we'll need to lift it is mg, and the distance we'll need to travel is the height. So we'll have our mass of 10 times g of 10 times our height of 5, which will give us 500 joules. Incidentally, you could look at that and say, hey, that's the potential energy equation. Hang on to that. Good eye. Great. So for the next part, for the work equation, if there's calculus involved. If it is a variable force, the equation is much the same, but you do actually have to take an integral of the thing. If the angle is constant, feel free to pop in a cosine theta, but because the angle isn't changing, you'll be good to go to treat it like a constant. If the angle is changing, you need to find a way to represent dx in terms of theta, or theta in terms of x, or cosine theta in terms of x somehow, so that you can eliminate the multiple variables before you take an integral. You basically need to use related rates to get the two related to each other. I'm not going to have an example of that one because I don't. But if it comes up, I'll be available and very interested in providing help for it. And I don't think I've seen that on the AP exam, but it could theoretically exist. Make sure you take the integral over the full range of motion, so start from the start location, go to the end location, whatever that may be. Hopefully this will make more sense with an example problem, but basically you just integral of f dx, you would need a f as a function of x. So figure out what that function is, or you'll just be given it. For this next problem, how much work is done by someone who lifts a chain of length L and mass m from a table until it's just barely off the table at a constant velocity. This one we're going to have to make our own equation. So let's hop to it. We've got our chain. It's on a table. The force required to keep the amount of the chain that's off of the table is going to be equal to the weight of the chain that's off the table. So the mass that's off the table times g. We'll need to pull it up with the same amount of force. So F1 will need to equal mass that's off the table times g. And if I define this distance to be my x, then what that will be over here is going to be, if I take x and I divide it by the chunk of chain that's off the table, and I'm actually going to flip that. The mass of the chain that's off the table divided by the distance. That will need to be equal to the total mass of the chain, which is lowercase m, divided by the total length of the chain. If it's a nonlinear density chain, this changes, but if our chain is such that we've got sort of the same density throughout, then the ratio of any chunk of it compared to the whole will need to be the same, because that's how densities work. Linear densities, area densities, volume densities are going to come up a lot more later. Basic premise is just going to be that if you take something's mass and you divide it by some spatial component, that'll need to be constant throughout the object if it has a constant density. If the density has a function, you'll have to use the function. But for this one, just they're the same as each other. This is really nice because if I multiply each side by x, then what I've got is a function such that I have a function for force in terms of position, which is that like distance off the table, which is the distance that it's moving. which is that if I take the total mass and I divide it by the length, and I multiply it by the distance it's traveled off the table, and multiply that by g, that's how hard I need to be pulling it. The more of it's off the table, the harder I have to pull. Well, this is useful because now I can calculate the work, because work is equal to the integral of force as a function of position, dot producted with position. And if I take my stuff and I plug it in, work will be equal to the integral from 0 all the way up until the top of the chain for L. The bounds of integration here are fairly important. Of m over L times my distance times g, this is my function for force, times the dot product of x. Nice and easy integral here, thankfully. We've got m over L times x squared over 2 times g. That needs to be evaluated from 0 to L. And that'll be equal to m L squared over 2L times g minus our initial, which is 0. So, canceling out the L squared over L, we'll get mLg over 2. And what this is telling us is that we need to do enough work to do there's some points I can make involving potential energy. This is the potential energy of the center of bringing the center of mass to half the chain length above the table, or alternately you can think of it as the amount of energy, half the amount of energy you would need to bring the whole chain all the way up to the length of the chain. And if you look at the geometry of the situation, like when it's all the way up here, it's like taking this half and bringing it up to here, and taking this half and bringing it down to here, which should hopefully make some level of sense, that it's sort of like splitting the difference between bringing the part that you did all the way up as high as you did and the part that you didn't have to bring up up to the same place in the middle and having them meet. So there's some cool symmetry ways that you could have solved this one conceptually instead of doing the math out, but the math backs it up, and it is nice when that happens. Summarizing, make sure you're using the angle when you're doing the mg cosine theta thing. First off, it's cosine, not sine. Be careful about that. You want the component that goes the same way as the force, or the force that goes the same way as the distance that you're going. And for this one, you're going to, yeah, I mean, that's basically all of it. For this stuff, when you're taking your integral, just make sure you've got f as a function of x. Sometimes you'll have to think about it a little bit to get f as a function of x. Sometimes that might look like a density function. That's going to start coming up for this class, although not a lot this unit. That's much, much more in the unit where that comes up is mostly going to be the rotation unit. A little bit in the center of mass unit, the momentum unit, which is the next one. Once you've done that, just integrate over your full bounds of motion, and you should be good to go. A lot of times these problems wind up with things where you've got like weird length components on top, or like units on top which are being divided by other length units that should drop once you plug in your bounds of integration to get normal units. That's it. Goodbye, YouTube.